There is a moment that pilots who flew it describe in almost identical terms, regardless of when they flew it, or where they were based, or what mission they were executing. The moment comes somewhere in the acceleration sequence, after the engines have settled into their cruise configuration and the airspeed indicator has passed through numbers that no other operational aircraft in history has sustained in level flight. The moment comes when the pilot looks down through the canopy at the Earth below and realizes that the curvature of the planet is visible, not as an abstraction, not as something you know intellectually, but as a physical reality you can see with your eyes, the way sailors used to see it from the tops of masts before anyone had explained to them what they were looking at. At that altitude, in that aircraft, at that speed, the atmosphere below appears as a thin blue line, separating the dark of space above from the illuminated surface below. The pilot is not in space. The aircraft needs air to breathe, needs air for combustion, needs air for the wings to generate lift. But the pilot is at the edge of space, in a way that only a handful of aircraft in history have reached. And the SR-71 reached it routinely on operational missions every time it flew. No aircraft flying today reaches that altitude on a regular basis. No aircraft flying today sustains those speeds on operational sorties. No aircraft flying today has matched the combination of altitude and velocity that the SR-71 achieved as its normal operating condition. The aircraft has been out of service for more than a quarter century, and in the specific domain of speed and altitude that defined its character, it remains unmatched. The story of how it came to exist runs through the Cold War's most anxious period, through a design process of exceptional originality, through operational deployments that accumulated records and absorbed losses in roughly equal measure, and through the institutional battles that ultimately removed it from service for reasons that had more to do with budget politics than with any failure of the aircraft itself. It is a story about engineering at the extreme edge of what was materially possible, and about what happens when you build something that no adversary can catch and no budget process can easily justify keeping. To understand the SR-71 requires understanding what came before it, and what came before it was a program that most of the public did not know existed until decades after the relevant aircraft had been retired. The intelligence agency that ran American foreign intelligence collection in the 1950s needed a platform that could photograph denied territory from altitudes that the interceptor aircraft of the period could not reach. The solution was a purpose-built high-altitude reconnaissance aircraft, extraordinarily long-winged and light-structured, that could operate above the ceiling of contemporary air defenses. This aircraft worked for a period, and then it was compromised. The incident was public, the diplomatic consequences were severe, and the intelligence community needed to think about what came next. What came next began with a design office at an aerospace company that had a culture of doing things that other companies said could not be done. The design chief who ran this office had built the high-altitude reconnaissance aircraft, and he was already thinking about its replacement before the program that justified a replacement had officially begun. The direction of his thinking was straightforward in concept and extraordinarily difficult in execution. An aircraft that survived not by flying above the interceptors, which had caught up with the previous design, but by flying so fast that nothing could catch it. The design that emerged from this thinking was unlike anything in operational service. It was shaped by the physics of sustained flight at speeds exceeding 3 times the speed of sound, a regime in which the aerodynamic heating generated by air friction raises the aircraft's surface temperature to levels that aluminum alloys cannot withstand, and that require materials whose primary characteristic is thermal resistance. The design was also shaped, from the beginning, by the requirement to reduce radar detectability, not to the levels that would be achieved decades later in purpose-built stealth aircraft, but to levels that complicated the task of any radar operator trying to track an object moving so fast that the tracking geometry alone was challenging. The configuration that resulted from these constraints was a broad delta wing with distinctive chined edges, the forward fuselage having a flattened cross-section that blended aerodynamically with the wing surfaces rather than sitting above them as a conventional fuselage would. 2 large engine nacelles were embedded in the wing rather than hung beneath it or beside it. The entire profile was low and wide, presenting a shape to ground-based radar that was smaller than the aircraft's actual size, and that did not correspond to the characteristic signature of any known aircraft type. The material that made this possible was titanium, specifically high-strength titanium alloys that could maintain their structural properties at the elevated temperatures that sustained Mach 3 flight generated. The airframe was approximately 85% titanium by weight, and building it required solving manufacturing problems that had not previously existed, because nobody had tried to build anything remotely similar at this scale. Titanium is difficult to machine, and difficult to work at the large dimensions that airframe construction requires. The supply of titanium in the quantities the program needed came through arrangements that were themselves classified, because the primary source of high-grade titanium ore available in sufficient quantity was a country that the aircraft was being built to gather intelligence on. A geopolitical irony that the people running the program were aware of and could do nothing about. The engines that powered the aircraft were themselves a development program of exceptional complexity. The combination of a turbojet operating normally at low speeds and in the subsonic regime, transitioning to a configuration that captured the ram air compression generated by supersonic flight at high speeds and used it as a primary source of thrust, required an engine design that functioned differently at different points in the flight envelope. At takeoff and landing, the engine was a conventional turbojet. At cruise speed, it had transitioned to a hybrid configuration in which the inlet captured supersonic airflow, compressed it through a variable geometry spike that moved automatically with speed, and fed it into the combustion chambers in a way that allowed the engine to generate thrust at speeds where a conventional turbojet would have been unable to function. The fuel that the aircraft burned was itself a specialized compound, a thermally stable kerosene formulation developed specifically for this application, because the heat generated by aerodynamic friction during high-speed cruise raised the fuel temperature inside the tanks to levels that conventional aviation fuel could not tolerate without decomposing. The fuel served a secondary function as a structural coolant, circulating through elements of the airframe and absorbing heat before it was burned in the engines. At ground level, the fuel was sufficiently stable that the aircraft's known tendency to seep fuel through airframe joints was not considered a safety hazard under normal circumstances. The material would not ignite from a spark or open flame at ambient temperatures. At operating altitude and speed, the situation was entirely different. The airframe's relationship to thermal expansion was built into the design in ways that created the unusual characteristic of intentional leakage on the ground. The aircraft was sized for its cruise condition, the temperature at which sustained Mach 3 flight held the structure. At ground temperatures, the structure had contracted from its design dimensions, leaving small gaps at panel joints and structural interfaces. These gaps closed as the aircraft heated during flight. On the ground, they were open, and fuel that filled the tanks to operating levels would seep through them. Ground crews accepted this as normal operational behavior, soaking up the spillage and working around it, because the alternative was designing an aircraft that fit at ground temperature and developed structural problems when it expanded to operating temperature. The operational profile that the aircraft used was itself a consequence of the weight that Mach 3 performance required. To achieve the design speed and altitude required an aircraft heavy enough with fuel that taking off with full tanks would have exceeded the structural limits of the landing gear and the runway surfaces available. The aircraft therefore took off with partial fuel, enough to reach a tanker aircraft that waited at a pre-briefed rendezvous point, refueled to full tanks in the air, and then accelerated to cruise speed and altitude for the mission itself. The same sequence was repeated in reverse on return, unless the mission duration and the destination allowed return with sufficient fuel margin without additional refueling. This dependence on aerial refueling was operationally significant because it meant that every mission required coordination with tanker assets, and the tanker aircraft operated at speeds and altitudes that required the faster aircraft to slow down substantially for the actual fuel transfer. The transition from Mach 3 cruise to refueling speed and back imposed thermal cycles on the airframe that accumulated structural fatigue, and the total number of such cycles an airframe could sustain before requiring major maintenance was a factor in planning operational tempo. The aircraft that the military aviation branch eventually designated the SR-71, the designation resulting from a sequence of institutional decisions and possibly a presidential misreading of index letters that has been debated since, was not the first of its design family, but it was the largest and most capable member. The reconnaissance aircraft that the intelligence agency had operated was optimized for a single-seat crew and a specific intelligence collection mission. The military version was sized for a two-person crew, with the second crew member responsible for operating the reconnaissance systems, and it was configured with a more flexible equipment architecture that allowed the mission payload to be changed between sorties. The second crew position created an engineering challenge that required significant redesign of the internal layout. The space immediately behind the pilot's cockpit, which the single-seat version used for primary equipment bays, was occupied in the two-seat version by the second crew position.
The reconnaissance equipment had to be relocated and reorganized, and the solution, a modular nose section that could be configured with different sensor packages for different mission types, turned out to be a design approach sufficiently useful that it influenced subsequent reconnaissance aircraft programs. The sensors that the aircraft carried represented the state-of-the-art in airborne intelligence collection at the time of the aircraft's introduction and were progressively updated as technology advanced. Optical cameras provided photographic imagery. Radar systems using synthetic aperture techniques produced ground imagery that was not dependent on lighting conditions or weather. Electronic intelligence systems collected signals across the radio frequency spectrum. Infrared sensors detected thermal signatures. The combination allowed a single aircraft flying at speeds and altitudes that made effective interception essentially impossible to collect comprehensive intelligence across a wide swath of territory on a single transit. The navigation system incorporated stellar tracking, a sensor mounted behind the second cockpit that used the positions of stars to verify and correct the aircraft's inertial navigation system. The requirement for stellar navigation in an aircraft that flew in daylight as well as at night was accommodated by the high altitude of cruise operations, where the sky above is dark enough for stellar observation regardless of the time of day at ground level.
The sensor received an informal designation among crews that referenced a fictional robot from a popular entertainment franchise, an acknowledgement that the technology, developed originally for missile guidance applications, felt more appropriate to science fiction than to a machine that was taking off and landing at operational airbases. The aircraft entered service and began accumulating the operational record that defined its reputation.
The characteristic pattern of that record was missions over denied or contested territory, where the combination of speed, altitude, and reduced radar signature made successful interception essentially impossible, with the technology available to adversaries throughout most of the aircraft's service life. Hundreds of surface-to-air missiles were fired at the aircraft across its career. None hit. The geometry of the intercept problem, an aircraft moving at better than 1 kilometer per second at an altitude above the effective ceiling of most weapon systems, meant that a missile fired at the aircraft's current position arrived at empty air because the aircraft was no longer there. Vietnam provided the first sustained operational experience. The aircraft flew from a base on a Japanese island to the conflict zone and back, coordinating with other aircraft operating the single-seat version of the same design family. The air defense network that North Vietnam had constructed with Soviet assistance was among the densest in the world at the time, and it found the SR-71 essentially untouchable. Pilots reported observing missile launches in their rear-view mirrors and watching the weapons fall behind as the aircraft continued to accelerate away. The psychological effect of being untouchable, of knowing that the weapons that would have been lethal to any other aircraft in the inventory could not reach you, was something that crews described in terms that suggested it was both reassuring and slightly surreal. The informal name that crews gave the aircraft during the Asian deployment came from a venomous snake native to the island where they were based, a creature with a reputation for being difficult to see, difficult to avoid, and dangerous when it struck. The name spread through the crew community and persisted through the aircraft's operational life alongside the official name that referenced the aircraft's coloration and shape. European operations were conducted from a base in England, with sorties along the edges of Warsaw Pact territory. The operational philosophy in the European theatre differed from the Asian deployments. The aircraft generally did not penetrate Soviet airspace, operating instead along the borders and collecting intelligence from standoff distances where the high-resolution sensors could still acquire useful information. Occasional brief airspace violations, when navigation errors or mission geometry required them, were brief enough and fast enough that Soviet air defenses could not mount an effective response before the aircraft had departed. One incident that became part of the aircraft's folklore involved a mechanical problem that required the crew to descend from cruise altitude and slow to subsonic speed. Exactly the flight regime where the aircraft's performance advantage disappeared, and where Soviet interceptors could potentially engage it. The situation resolved when Allied aircraft provided cover during the recovery, and the aircraft landed at a friendly nation's base rather than attempting to reach its home field. The outcome was operationally satisfactory, but the incident illustrated that the aircraft's invulnerability was conditional on its ability to maintain its design performance. Middle Eastern operations provided a different kind of experience. Photographic and electronic intelligence collection during the various conflicts that defined the region's history during the aircraft's service period. The aircraft's ability to transit large distances at high speed and collect comprehensive intelligence on a single pass was particularly valuable in a region where the political geography made sustained presence of slower aircraft diplomatically complicated. The aircraft's record-setting flights accumulated through its service life
with a matter-of-fact quality that distinguished genuine capability from demonstration performance.
The New York to London transit time that the aircraft achieved was less than half the time required by the supersonic commercial airliner that had represented the fastest passenger service available. The sustained altitude record during level flight exceeded 25 kilometers. The speed record for a jet-powered aircraft in sustained level flight was set at a velocity that no subsequent aircraft has exceeded in regular operations. Pilots who pushed the aircraft toward the edges of its performance envelope reported that there were reserves that the official performance numbers did not fully capture. Accounts of temporary excursions to speeds beyond the documented maximum appeared in memoirs and interviews with the consistency that suggests operational reality rather than embellishment. The aircraft was built with margin, as serious aircraft always are, and the margin appears to have been occasionally accessed in circumstances that justified accepting the additional structural stress. The case against the aircraft's continued operation was made primarily on economic grounds. It was expensive to build. The unit cost was substantial even by the standards of high-performance military aircraft. It was expensive to operate. The maintenance requirements per flight hour were dramatically higher than those of any other operational aircraft, reflecting the specialized materials and systems that Mach 3 capability required. The infrastructure needed to support it, the specific fuel, the specialized maintenance personnel, the facilities equipped for handling an aircraft that operated at temperatures most maintenance equipment was not designed for, added to the cost in ways that were difficult to quantify but impossible to ignore. The argument that satellites could perform the same reconnaissance mission more cheaply and without risk to a crew was made repeatedly and with increasing force as satellite technology improved. The counter-argument that satellites followed predictable orbits that adversaries could work around, that atmospheric penetration introduced uncertainties that the aircraft did not face, that the aircraft could be redirected in real time while a satellite could not, was also made repeatedly, and the debate was never fully resolved on purely technical grounds, because the answer depended on specific circumstances that changed with geography and mission type. The first retirement came in 1989, at a point in the Cold War's final stages when defense budgets were beginning the process of contraction that the conflict's apparent resolution made politically available. The decision was made by people who controlled the budget rather than people who flew the aircraft or depended on its intelligence products, and the community of people who had worked with it responded with the specific frustration that comes from believing a capability is being abandoned for reasons that do not fully account for what is being lost. The frustration proved justified within 2 years. A conflict in the Middle East created exactly the kind of rapidly evolving intelligence requirement that the aircraft had been designed to address, and the aircraft was not available. The gap was filled, imperfectly by other means, and the operational commanders who needed information and could not get it as quickly as they needed it made the case for restoration with the authority of people who had just experienced the absence of a capability they had previously relied on. A limited restoration followed, not a full return to operational status, but a partial reconstitution that put a small number of aircraft back in the air for a period that lasted through most of the decade. The restoration was never treated as permanent, and it ended as the arguments about cost and the availability of alternative systems reasserted themselves. The final operational flights came in the late 1990s, followed shortly afterward by the conclusion of the scientific research program that had extended the aircraft's career beyond its military utility. The aircraft that remain are in museums.
They sit in the specific posture of aircraft on display, static, grounded, lit from above. And the combination of their size, their shape, and the knowledge of what they did gives them a presence in museum halls that most displayed aircraft do not have. Visitors who stand beneath them and look up at the black underside and the distinctive chined nose are looking at something that the designers of every subsequent aircraft have had to reckon with, because no subsequent aircraft has achieved what this one achieved in the specific domain that defined it. Speed and altitude are not the only dimensions of aircraft performance that matter, and in many operational contexts they are not the most important dimensions. Stealth, sensor capability, weapons integration, connectivity with other systems. These characteristics have come to define the most capable aircraft of the subsequent generation in ways that suggest the direction of development has moved away from the approach the SR-71 represented. An aircraft that survives by moving faster than anything that might threaten it is a different design philosophy from one that survives by not being detected, and the latter philosophy has proven more adaptable to the full range of operational requirements that modern air power faces. But there is a specific kind of performance, the performance at the absolute boundary of what physics and materials permit, that the SR-71 achieved and sustained across 3 decades of operation in a way that no subsequent aircraft has replicated. The boundary has not been approached again in regular operational service. The altitude that produced visible planet curvature remains accessible only to aircraft that are not aircraft in the conventional sense, and to the SR-71, which reached it on missions and returned and was serviced and sent back up again, routinely as a matter of operational practice. The pilots who flew it knew what they had. The engineers who built it knew what they had made. The people who decided to retire it made a reasonable decision by the criteria they were applying, and the people who argued against the retirement made a reasonable argument by the criteria they were applying. The aircraft itself was indifferent to both arguments, as aircraft are, and it flew until it stopped flying, and then it stopped. What it did while it flew has not been done since.